Hey everyone, I'm Joel Greene and welcome to Curiosity Quest, the show that explores what you, the viewer, are curious about. Now today, our quest setter came to us from Pittsford, Michigan. Tristan wrote, "Dear Joel, I'm curious, how do they make solar panels?" Well, Tristan, because of you, we're out here in Hillsboro, Oregon, home of Solar World. We're gonna learn how they make solar panels. So let's begin today's Curiosity Quest Goes Green. All right, so we're inside Solar World, and I'm here with Marvin. Good to meet you this morning.
Good morning.
Tell us a little bit about Solar World. How long have you been here, and what are we going to be seeing today?
Solar World's been in existence for about 37 years. We're one of the largest American-made manufacturers in the U.S. for solar panels. What you're going to see today is wafer fabrication through the final cell manufacturing and then into the module manufacturing. The process starts with raw silicon.
Raw silicon?
The raw silicon is the most abundant mineral on the planet Earth. So we take raw silicon.
Wait, what is silicon?
Silicon is basically sand.
Sand?
It is basically sand. Very high purity silicon. We will take it, put it in a crucible, melt it down, and we grow it just like growing a candle. So it'll grow at a 6-foot tall ingot. We will chop it into a wafer, which is about the thickness of a human hair. And then we'll take that wafer and we do our silicon nitride treatments, our diffusion processes, and we create a solar cell.
All right, so we're getting really technical here right off the bat too, which I assume that's probably a lot of your process is, a real technical process, right?
Very.
Fun fact, fun fact, fun fact. Here's your fun fact.
Did you know that Albert Einstein won the Nobel Prize in 1921 for his experiments with solar energy?
What am I looking at right here?
Okay, this is a good overview of how we start. So if you start over here with the crucible, that's a crystal crucible that we put the raw silicon in. We heat it up, get it to temperature, and we start growing this 6-foot tall ingot of silicon. It looks like a big candle, and it's basically the same process of candle growing. We then take that ingot, we cut it into our finished dimension for the wafer. We use a wire saw to cut it into the thickness, which is about the thickness of your hair for the wafer, and then we move that wafer over into the cell process. Right now, we're doing our wafer, our cesium wafer growing in Germany, and we will do the cell and the module manufacturing here in Hillsboro.
Okay, so once we have the wafers, basically now it's in your hands.
Now it's in our hands and we can take it from there.
All right, so this is where we get all goggled up.
This is where we go put on the bunny suits.
So are we ready to go in
We
now?
are ready to go.
So everything's covered out like
You are covered, you are 5 by 5.
Bunny suits, I love it. All right, let's do it.
Let's go.
What is silicon?
Trash can.
Something that attracts light.
The material you use to make computers?
Plastic part, the holes, they won't leak out when you turn it upside down.
Kind of like, I guess like what's in solar.
A boogie.
Marvin, what is silicon again?
So again, silicon is the most abundant mineral on the surface of the earth.
So silicon or silicon?
Silicon.
Silicon, okay.
So it's basically, if you look at sand, that's a pretty pure form of silicon, but we use an even purer form for the module, for the cells that we have to manufacture in solar panels.
And where does that come from again?
So we have a couple of mines that we source that silicon out of that gives us the purity that we need to be able to make solar cells.
So it comes out of the ground.
Comes out of the ground,
Okay.
yes, ma'am.
And so once you have those ingots and we've chopped them down, these are the hair.
Hair thick, so about the thickness of your hair. These wafers are going to come down. Each one of the red cameras is looking for that overall wafer dimension to make sure we don't have any cracks, any chips, any damage. What we're going to do next, so we talked about that saw, that wire, piano wire going through the wafer, cutting these hair thick wafers. Now we got to remove that edge damage. All those little wires created little surface deformations that we need to make a nice smooth surface. So this bath that you see behind me is going to remove about 8 microns on each side of the wafer. Yeah, a very tiny
Show me what an 8 micron is. You can't, can you?
Your hair is 180 microns, so just imagine we're taking just a sliver off of each side to make sure we have a nice smooth surface to be able to build the solar cell out of.
Are we doing this with laser or with?
It's a chem etch bath. So it is a chemical bath that we're going to push it through. It's going to etch off material off both sides.
So we can't even see that being done, right?
No.
It's, wow. All right, Marvin, what do you have in, wow, in this hand? What do we have?
So on the left hand is where we have removed the saw damage from the silicon wafer. What we have here is the next process where we're actually going to create a mirror surface on the back of the wafer to capture as much energy as possible and increase the solar cell power. So as you see, we only create this mirror surface on the back side of the wafer.
So this isn't the side that's facing the sun?
That's the sunny side.
Oh, and why are you doing that again?
For energy absorption. So we're going to create like a mirrored surface, going to bounce as much of that energy as possible back into the active area of the cell.
This mirror surface that you're talking about appears gold. Is that the way it is on all of them?
Well, yes. For our mono-PERC process, they're all going to have that same PECVD surface finish to give us that power generation, that reflectivity into the actual of the cell.
Now, I noticed there's some like little burnt ends on the side.
So those are areas where the carrier is shielding the treatment on that cell.
Oh, okay.
So you're going to see behind me the automation as it's loading these wafers into those carriers. There are going to be points where the wafer is going to physically make contact with that carrier, and that area is going to be shielded from our treatment of the PECVD process.
I see this light flashing behind me. Is it literally like spraying it on there?
Nope. Actually, it's being treated behind us in a process. What you're seeing behind me is additional inspection. So you're going to see cameras going throughout the process. They're just verifying each stage of the process. We don't have any cell damage. Our processes are consistent, that we are producing a repeatable process, wafer after wafer, cell after cell.
So to actually put this on there, is that a proprietary step?
That is a very proprietary process.
I'm getting at it because you haven't volunteered it, so.
So the next step, we're actually going to create a pyramid surface on the sunny side, which will increase the surface area of that silicon wafer.
I'm just curious, right now, if you flip that over, is it catching the light, creating energy?
Well, yes. So all silicon, when you bombard it with light, and it's going to have that energy absorption. It's going to create that electron flowing, that current flow, but it's not a very efficient process yet. We still got to build that p-n junction. We still got to build it up.
Wow, tech talk. All right, so let's move on to the next step. All right, be careful with those.
Absolutely.
What shapes end up being on the solar panels?
Circle, squares,
A rectangle? Square and rectangles.
square,
Rectangle,
Squares, rectangles, or triangles? Cubes?
All right, Marvin, what are we looking at behind us?
All right, so once we got that mirror on the back of the wafer, the next thing we want to do is we're going to do texture. So what texture does, it creates little pyramid shapes on the surface of the silicon, on the sunny side surface of that silicon. And what that does, it increases the surface area of that cell, gives us more power.
So when you say pyramid shaped, they're pretty small, aren't they?
About 5 micron high, so very, very tiny pyramids across the entire surface of that cell.
And how does it do that? I mean, how are they?
So there is
put
an
on there?
etching process. It's a proprietary etching process that we use.
Meaning we can't see it.
Means I could tell you, but I have to hire you.
You don't want to hire me, I promise you that.
So it's going to pick up the carriers and take it through one bath after the next to start to create that pyramid surface into that silicon.
If I understand it correctly, if you have the wafer, it's basically etching into the wafer right now.
It's creating row after row of little bitty pyramids on the surface of that silicon.
That is crazy. And it's so small we can't even see it.
You can't see it. If we put it under a magnifying glass, you'll see it.
Can you tell us how many pyramids are being put on one wafer?
God,
Oh no, we need the answer now.
It's thousands. It's thousands of pyramids. What you're basically trying to do, when the energy from the sun impacts that silicon, frees that electron, creates that charge, the more silicon we have exposed, the more charge we can get, the more power we can get. So we're just trying to increase the surface area of that silicon by creating those pyramids.
All right, so after you have the little pyramids on the wafers, what next?
So after that, we have to create these laser holes where we're actually going to infuse the silicon to be able to get that power and create more power out of that cell.
This is crazy. My initial thought of solar panels is, oh yeah, you just take a shiny piece, point it at the sun, and you're good to
Just
go.
like that, you've got power.
You've got power,
There's a
yeah.
little more engineering than that.
Well, apparently so. How many steps are there to making a solar panel?
10, 5, 1,500. 10, 20, 6.
I don't know. You need the board, you need the panel, you need the little squares that go inside the panel. Wires, I don't know. The sun is one.
I can't believe how many steps I've already seen, and yet we're just partway through the process, right?
Hey, you're about halfway through the cell fab process. So there's about 8 big steps for the cell fabrication process, but each of those 8 steps can have as many as a dozen sub-processes underneath them.
And that's not even the module side.
Yeah,
right?
we haven't even gotten the module yet.
Oh my goodness. So how many steps would be there?
So there's another dozen steps in moduling, and again, each one of those steps can have sub-steps as well.
It's warm back here. What are we looking at?
So this is diffusion, and the reason it's warm is behind us there's a couple furnaces that are blasting about 800 degrees. So we're building another layer on that cell. So we talked about building those junctions within the cell to be able to get that power to the grid. So behind us, we have a couple different tubes that are furnaces that are running at over 800 degrees, and then we inert them with some very specific gases.
And so the gases are just basically, it's another layer that's going
Baking
on
on
top.
another layer.
And what's crazy is this layer, it's not like it's, growing like this. We can't see it growing with the naked eye. I mean, it's very small.
Microns.
Microns. You keep using that word microns.
So a byproduct of the diffusion process creates this thin layer of phosphorus glass. So we have to remove that layer
Oh.
so that we can put our silicon nitride treatment on it.
Okay, so we're adding a layer, then we're gonna take off a
We're
layer.
adding a layer, we're gonna remove a section of that layer so that we can add another layer on top of it.
Wow, all right. And then after you add that other layer on top, what do you do then?
Then we get to print solder paste into all those contacts so that I can take all the current in that cell and wire it to the grid. It's like a silk screening process, but instead we're printing metal onto the cells.
Wow. Can we go see that?
We will.
Fun fact, fun fact, fun fact. Here's your fun fact. The most abundant mineral in the Earth's crust is silicon.
So I jumped ahead. I was ready to put the metal on it, and you're saying, whoa, whoa, whoa. We have another
One
step.
more process. So we've got to do the silicon nitride treatment. So you're going to see after we remove that glass phosphorus layer, the automation is going to load up this carrier. We're going to feed it into a tank where we're going to create this blue, pretty blue hue silicon nitride treatment. And that flash you see, every one of these cells coming out is going to be treated for, we're testing to make sure we have consistency in color so that when we put these in a module, they all look the same throughout.
I'm sorry, I'm a little distracted by all the movement behind you here. Whoa!
So you're going to watch the automation, and again, they're placing to within microns of placement accuracy so that we're not causing any damage to these cells. It's going to load that carrier up. That carrier is going to feed into some high pressure vacuum furnaces, and we're going to just position the silicon nitride treatment, that nice purple orange hue that you see on these cells.
This is crazy. I'm seeing movement, I'm seeing flashes, and in this blue box right here, that's where that blue color is going on,
So
right?
it goes into this carrier, into the furnace, and then it feeds back out. And when it comes out of the silicon nitride process, it has this pretty purple hue color to it. That camera is inspecting for that cell consistency and color.
Wow. All right, so this is the blue.
So that's what it looks like. That's what the solar cell looks like after we do our silicon nitride treatment.
So
the next step after this, we get to print the solder paste into those patterns.
Into these patterns. So this is, the blue is just a silicon nitride?
It's a silicon nitride treatment, and it's an AR coating that we put onto the cell to give us more power.
More power. Wow.
Building another layer.
Oh my
Another layer.
goodness. Lasers and pyramids and chemicals and, oh, wow. All right, so now we're going to put the
Now
metal
we
on.
print the paste onto that, just like a screen print. So we are going to print just like a t-shirt silk screening process. We're printing metal into that contact area. We're going to fire it in our firing furnace, and then over in the next stop module, we're going to solder ribbon to that metal contact to be able to take the current flow to the grid.
Unbelievable how many steps. So it's not a very thick layer though, is
It's
it?
a very thin layer of paste that we're printing in there for our electrical contacts.
And now we're going to go put the electrical contacts down?
Well, once we do the firing furnace on the both the sides, so we're going to print on one side, we're going to print another side, we're going to put an aluminum layer on the back side of the cell. Then we go over to the module.
So you actually, this goes on both sides?
It goes on both sides.
Oh, wow. So it flips over
Oh,
at
yeah.
some
You're
point?
gonna watch, you're gonna go through the firing furnace, cure it, flip it, we're gonna print the back paste, and then we're gonna print an aluminum layer, and then we're gonna fire it, and then it goes to module.
All right, cool. What is a watt?
It's what you use to measure light bulb energy.
A wasp.
Oh, wow.
To slap flies.
Oh, it's like a fly swatter.
Nothing.
Nothing?
Nothing.
Certain kind of bug.
Something you use to recycle with?
Energy. 1 wattage to make it go. Electrical.
All right, when it comes to electricity, what's a watt?
So imagine when you're at your house, you turn on the faucet, you get water pressure out of that spigot.
Okay, like how hard it's hitting
How
you?
hard it's hitting and how much water's coming out of that nozzle, that's water pressure. So a watt, imagine we're trying to measure how much current flow we're getting out of a cell, and we associated it as a watt, as a wattage for each one of those cells. So that's how we're measuring how much power we're getting out. Each one of these cells is by wattage.
By wattage. And how many watts will a wafer, collect?
So each one of these wafers is over 4 watts per cell.
It doesn't sound like very much.
But when you stack it up into a module, right now, our standard 260 cell module, we can make a 275 or a 280 watt cells.
Is this the final step in the wafers right now?
This is the final step in cell manufacturing.
I said keep calling them wafers. They're beyond wafers now,
Yeah,
right?
when we started, they were wafers. Now these are solar cells.
These are solar cells. Okay. Now what's happening right here behind us?
So right behind us is the tester. So the cell tester is going through and is measuring the power generated from each one of these cells, and it's sorting them accordingly by their different power classification. So when I take that cell and put it into a module, we get a very tight power distribution. We know exactly what power we'll get out of that module when we microbend these cells.
So some will be over 4, under 4?
Right.
All right, so after you put them all in their correct bin, and what do we do now?
So the next step, they're going to get packaged up in these styrofoam containers, and we ship them over the module for their final assembly.
So are we heading over to the module?
That's next.
Let's go do it. How long has solar energy been around?
10 years?
Since the 1800s.
199 years.
For about 20 years.
5 or 10 years. I don't know, 10, 20?
For years, a lot of years.
Since the 80s.
Are we talking 1980s or?
80, yes.
All right, so we have our cells that we brought over now, huh?
So we've got all the love our brothers across the street put into these cells, and we're handling them with kid gloves. So the automation is picking up the cells, placing them on that white belt, where we're going to do an additional inspection in that black box, and we're looking for cell quality, make sure we don't have any damage. That metal that we printed onto the cells, we're now going to take this ribbon and solder it to those metal contacts to get that current flow off of the cells. So it's just like building a battery. We want the current flow to go from the bottom to the top, So you're going to watch the ribbon being pulled and crimped and layered over each upcoming cell. Then we're going to solder it on that brown belt.
So they're all being connected at this point.
They're all being electrically connected. We're soldering that ribbon into that cell, and then we're going to do a pull force test on it to make sure that we've got adequate adhesion. So we actually measure how much force it takes to pull that ribbon off to make sure we have consistency throughout our process.
How many will you connect together on a panel?
Each string is going to have 10 cells. So you're going to see 6 different strings with 10 cells each on our standard 2 product. So right now, we're building that string of 10 cells. The ribbon and the solder isn't soldered at this point. What you see here, the automation is soldering that ribbon into the cell. So we're making an electrical connection from that ribbon into the cell now for current flow.
And they're all connected. I see it looks like what?
So after this process, that string is electrically connected. It's all soldered together. It's one solid mass. So next up, we will do another inspection to check for the overall cell length. The robot will then pick up that standard 2 string, places it on the green belt like so.
Whoa, coming right at me, man.
Next step, we start building the matrix.
Okay, when you say building the matrix.
So right now, I've got 10 cells in a single string. I need 6 strings for a 60 cell module.
Gotcha.
So just like a battery, every other string, I'm gonna turn it 180 degrees.
All right.
Current flow. So if you come down, you'll watch the automation pick up the string, takes it over, aligns it, trims it, and it starts to place it on that sticky black tray.
Yeah.
That tray is made up to make sure that the matrix doesn't move, that we have a very consistent placement and it doesn't move while we're handling it.
I noticed that the arm that just came over here, the first one it set down, it flipped it around.
Exactly. Current flow.
Oh, I
So
get it.
just
So
like a battery, every other string has to be turned 180 degrees
I
for
got
current
it.
flow.
That one just turned again. The one prior, it stayed
right.
the same. That makes sense. So are they connecting at the ends?
At the ends. So the next step after this, we're going to solder a bus bar to the ends, and you're going to have 4 terminals that are going to come out of the module, which we will then solder to our junction box, which will take the current to the grid.
Okay. So for those of you at home, that just took me a while to catch on. So obviously you have those the metal points sticking out, and each one of them, like the energy was going this way, the flow was going this way.
The energy is flowing down. We will rotate it around. We're going to solder bus bar to the bottom to be able to complete the circuit.
The next one, the energy is going up. Next one, the
one's
energy is
coming
going
down.
down. Next one, the energy is going. Ah, that's crazy. Cool.
Fun fact, fun fact, fun fact. Here's your fun fact. Earth receives more energy from the sun in 1 hour than it can use in an entire year.
So it looks like we're pretty much done, right?
Well, we've built a laminate at this point. So once it goes through the lamination, high temperature, high pressure, EVA becomes translucent, squeezes everything together, seals it all up. Next, we're going to put a J-box on the back to get all the power out. Junction box.
You said laminate, just like you would laminate something at school.
Just like your driver's license, your student IDs, that's a laminate.
And it's all sealed now.
High temperature, high pressure bladder squeezes on it,
Yeah.
gets it up to temperature, becomes translucent, seals it all out.
Now, at this point, by the way, you can see I can actually touch something now, which is good, because I can't hurt it at this point,
cannot
right?
hurt it.
Okay, and that EVA is on top of this.
So the EVA, you got glass. This surfaces the glass.
Yeah.
We have a layer of EVA, the cell, a layer of EVA, and the back sheet.
The back sheet obviously just looks like this.
Right.
White piece back there. But now, I mean, we're almost ready to throw it on a roof, right?
It is real close to being an actual module right now.
Okay. Well, but right now it's just a coffee table. is what
Right
you're
now it's
saying.
just a laminate. There's no power going anywhere.
Or a flooring, or a shield, or a roof. I'm just making it up, right?
Shingles.
Shingles, very expensive shingles. So we're at the final stage now?
Final inspection. So it's a module. We've measured the power. We put a power label on it. We've dispensed silicon, closed up the J-box, the junction box where we're going to get the power out. We're doing our final grading. We're going to close up that J-box.
Is that liquid in there? Or?
So it's kind of like pudding. Imagine a very thick silicon pudding-based material that we pour into these J-boxes with our automation to make sure that we seal out any moisture.
Okay. And you were saying too that you flash the
We will simulate the sun is what we do, and then we measure the wattage coming off of that module for a specified amount of time. That's how we know that we're going to make a specific power class for that particular variant.
How big is a micron?
Smaller than a germ, I guess. A house.
Whoa.
15-story house.
Have you ever seen a 15-story house?
No.
Wow.
A what?
Wow.
A mouse?
2,000 feet tall.
The building?
Very, very small.
About 5 feet.
All right, Marvin, we're outside, and a question that I have for you, I'm sure you probably get this a lot. We're here in Oregon. It is cloudy. Are these working properly in the clouds?
Even on a cloudy day, we're still getting enough power from the sun to be able to make a decent amount of wattage out of these panels. The climate in Oregon is better than it is in Germany, which was the largest solar panel installation on the planet. The Southwest U.S. is so prime for the panel generation and panel production. It is primo property for solar panel installations in the Americas. The entire country is good for solar.
Marvin, I want to thank you so much.
Thank you for coming.
Very educational. I want to thank him and everyone here at Solar World for teaching us how they make solar panels. And I especially want to thank you, Tristan, for sending us on today's Curiosity Quest Goes Green. Now, if there's something you want to know more about, let me hear from you. Go to curiosityquest.org, click on the Send Us on a Quest link, and simply tell me what you're curious about. And it could be you that sends us on our next green adventure. Now remember, this is our planet, and it's our responsibility to take care of it. So I wonder, have you gone green? I'm Joel Greene, and I'll see you next time. Wow, I really need to brush up on my science. Click on the Send Us on a Quest link and great adventure. Now remember, and simply click on the quest, and it could be you that sends us on our next journey. And remember, every great adventure begins with just one person's curiosity. So I wonder, what are you curious about? Keep it going.
If you'd like to order a copy of this episode or a previous episode, visit us at www.curiosityqueststore.com. The cost is $24.95.